this. So for every I, we can find mi rectangle covering Si, which total volume less than epsilon over k. Now, the rectangles Ij for I1 k, I from 1 to k, and the j from 1 to mi. These are m1 plus mk rectangle, finitely many. This number of rectangle covers the union of Si. We have for these rectangles, we have the following result. I from 1 to k Si is contained in the I from 1 to k, then j from 1 to mi. The right hand side of this inclusion, the right hand side looks complicated, but it is nothing. It is not nothing but the union of all these m rectangle. The sum of m1, m2, and k denoted by m. So the right hand side of our this is precisely the union of this m rectangle. They covers the union of Si, S1, S2, Sk. Okay, and also the total volume of this rectangle. The total volume of this rectangle is I from 1 to k, mi, j from 1 to mi. Okay, the inner sum is less than epsilon over k, so this will not is smaller than epsilon over k. So this is a sum of k terms. Each term is epsilon over k. Therefore, the sum is epsilon. So for any epsilon positive, we find m rectangles. We find m rectangles whose union contains the union of our S1, S2, Sk, and whose total volume is less than epsilon. Therefore, by definition, the union of S1, S2, Sk has Jordan content 0, proving our this second proposition. Okay. And also, we have the important property we need. If S has Jordan content 0, then for any epsilon positive, there are rectangles I1, maybe IM, such that S is contained in the union of the rectangle, and the total volume less than epsilon. This is the definition of Jordan content 0, but we can change the definition and obtain an equivalent description of Jordan content 0. That is the I here. The first condition requires that the union of this M rectangle contains S. This condition can be strengthened by requiring that the union of the interior of the rectangle. You can add a small cycle to II. That is the union of the interior of the rectangle contain S. Okay, so this is not difficult to prove. I don't know whether you understand what I am saying. So this is the definition. The definition requires that the union of this rectangle contains S, but I can replace this by requiring that the union of the interior of the rectangles contain S. We need this result. How can this be true? The idea is as follows. So this is S. We have a rectangle. The union of the rectangles contains S. Of course, the union of the interior is contained in the union, is a proper subset of the union of the rectangle. Therefore, the union of the rectangle contains S does not ensure that the union of the interior of the rectangle contains S. Okay, but you can enlarge every rectangle slightly. So intuitively, you enlarge the rectangle slightly. For example, for this rectangle, this rectangle, I enlarge this rectangle slightly to obtain this rectangle. Each rectangle you enlarge it slightly. Okay, then this enlarged rectangle, the interior of this enlarged rectangle, well, I denote it by I prime. So maybe no, I tilde. Okay, so the II will contain in I tilde, the interior of I tilde. Therefore, the union of I tilde contains the union of all the II. Therefore, contain S. Okay, so we can use the interior of the slightly enlarged rectangle, and the slightly enlarging the rectangle will not change the total volume too much. So you can require the total volume still less than epsilon. This is the idea to prove this description of a zero Jordan contained zero, that is replacing the union of rectangle by the union of the interior of the rectangle. This is very important in the proof of a theorem later. Okay, so I urge you to write the proof yourself, the detailed proof yourself after the class. Okay, now we consider an example. So example, let U be a bounded subset of Rn and closed, and f is a function continuous function defined over U. So f is an unvaluable function. This is Rn. So this is the graph of f. Okay, so the graph of f. The graph of f is the points of the form xfx when x runs through the domain of definition U. So the conclusion is that the graph of f has Jordan contain 0. Okay, so this is the an interesting example. I remind you that the GF, the graph, is a subset of Rn plus 1. Okay, our U is in Rn, but the graph of the function f defined over U is a subset of Rn plus 1 because x has n coordinate and fx has provided another coordinate. So the points in the graph has n plus 1 coordinates. Therefore, the graph is a subset of Rn plus 1. So we are required to prove that this subset has Jordan contained 0. Okay. So to prove this, we use the uniformly continuity of f Because the domain of definition U is bounded and enclosed, therefore sequentially compact. So F is continuous, therefore it is uniformly continuous. Since F is uniformly continuous, for any epsilon positive, we have a delta positive, such that Fx minus Fy absolute value less than epsilon. For any xy in U, the distance less than delta. Okay, this is the uniformly continuity. The second time we use the uniformly continuity. Now, consider this. This is our U. We take a rectangle I containing U. Take a rectangle I containing U. And suppose P is a partition of this I. Of our rectangle I. That is, this is the partition of the rectangle. Okay? Such that the diameter of each subrectangle less than delta. We take a partition of I such that the diameter of every subrectangle less than delta for any subrectangle belonging to this partition. Okay. Then let's have a look about what happened. Firstly, if the subrectangle has no intersection with U, for example, consider this subrectangle on the lower left corner. So this subrectangle contains no point of U. The intersection with U is empty. So for such subrectangle, we take Ij to be J Cartesian product of this J, which is a small interval. So J is an n-dimensional rectangle. The Cartesian product of J, which a small interval minus epsilon is n plus 1 dimensional rectangle. Okay, a lower dimensional rectangle Cartesian product with an interval gives you a higher dimensional rectangle. So this is denoted by Ij. So if the intersection is not empty, for example, we consider this rectangle in the middle of the upper corner, in red. So for this rectangle has no empty intersection with U. For such a rectangle, we can take a point in the intersection. Take a point here. This point is at Aj. Okay, so if this is our J, then we take a point. Since this J has no empty intersection with U, so we take a point in the intersection. So take a point Aj belonging to the intersection, and we defined Ij to be J multiplying Cartesian product with the small neighborhood the interval Faj minus epsilon Faj plus epsilon. Okay, so we see that every ij are rectangles in R n plus 1, and the total volume of such n plus 1 dimensional rectangle, total volume for every J belonging to the partition of I, that is P, the total volume, n plus 1 dimensional volume, because all the ij are n plus 1 dimensional rectangle. This is the volume of ij equals the volume of j multiplying the length of the interval. The length of the interval is 2 epsilon. Okay, so this is the n-dimensional volume of j under 2 epsilon. So this is equal to 2 vi epsilon. Here, the total volume of all the j is precisely the volume of I. So we obtain the volume of I here. And then we have 2 epsilon. So we conclude that the total volume of this rectangle is a number, a constant multiplied epsilon. Okay? If we can prove that the graph of GF, the graph of our function, is contained in the union of our rectangle IJ, so by definition, the graph has Jordan contained 0. So we need to prove that GF contained in the union of all the IJ for every J. Okay, we need to prove this. Okay, so let's prove this in the next page.